Thank you, everybody, for your patience. You know, it is PDE class. I hate to spend a day when we're not actually solving a PDE, but I do think that perhaps it's important to go solidify some theory and motivated by what we did last time. So what we did last time was we introduced this idea of writing a function, you know, on a closed interval from 0 to L with boundary values like equal to 0 on the endpoint. Could we write this function as a linear combination, infinite linear combination of functions of the form like constant times sine of like n pi x over L? And that led us to this kind of linear algebra idea of taking a vector space of functions. You know, can we take a collection of functions that's like orthogonal on that vector space and sort of in a way use them as like a basis, except instead of taking finite linear combinations, we take infinite linear combinations. And what we had looked at was, I mean, I looked at this vector space called V naught, you know, that included the boundary conditions, but more generally, you might look at some vector space V, which also has this funny terminology like L2 of the interval. And what this is like the collection of all functions. So sort of reviewing from last time a little bit, from the interval to R with the property that they are square integrable, meaning you integrate from A to B, the square of the absolute value of the function. And and this has to be finite. So the square of the absolute value has to be integrable, and the value that you get has to be less than infinity, so the integral has to converge. And that is a vector space, and I didn't prove it last time, and I still won't prove it this time. I'm going to kind of just give that one like maybe as an exercise or something, but I'll just tell you that it's true. You know, of course, the sum of two functions is what you think it is. Just add them up pointwise. Multiply a function by a scalar, that's still true. Certainly, if you multiply a function by a scalar, you just get like a constant c squared out here, right? So if f has this property, then c times f also has that property. And it's true that if you take two functions that have square integral less than infinity and add them together, then the sum will also be integrable and have, you know, square integral less than infinity. And so that's the one that's like a little technical to prove, so I'll skip it for this class, but it's completely true. So this is a vector space. It's called the L2 space on the interval from A to B. L is in honor of Henri Lebesgue, early 20th century mathematician who generalized the Riemann integral to a more general context. And so typically this integral is taken to be Lebesgue's integral, and there's like a whole story behind that, but the 2 stands for the square. So you could similarly do L3 or L pi or whatever, and then you just put another, you know, another number there. But I like to use 2 because when you're in L2, that's when you have an inner product, namely that product of fg is the integral f times g. And this is a legitimate inner product. And it satisfies those 3 or 4 conditions that we wrote down last time. And but for other values other than 2, then it's no longer true that this will give you like an inner product on the space, interestingly enough. You can also do this for complex valued functions. This just becomes modulus. And then the inner product would be f product with g is actually like f g bar but there's no need to do that here, I don't think. And the one small caveat is like I mentioned before, no, actually I'll say this later. So what I'll introduce next is you may remember that like if you have an inner product, you can then define what's called a norm. Use this notation for norm, and that's the square root of the inner product of the vector with itself. So in this case, it's going to be taking this integral now to the 1/2 power. And so this is called the L2 norm. So sometimes you put a subscript 2 there, or you put an L2 there. And I'll remind you the properties of a norm. So you are a norm if and only if the following things hold. So I'll use a dot just to indicate the input of the variable. So this is a norm on a vector space. I mean, I'm thinking about this very specific example, but generally speaking, take any vector space. You're a norm on that vector space if the following properties hold. So it has to satisfy what we call sublinearity. So the norm of v plus w has to be less than or equal to a norm of v plus norm of w. I just call this the triangle inequality. So this is like what the triangle inequality would say, like in R2 or R3, with your usual norm coming from the dot product. But more generally, you're a norm on a vector space if you satisfy this triangle inequality. So this is for all v and w inside a vector space v. Upside down A means for all. The second property you have to satisfy for being a norm is if you take a vector, multiply it by a scalar, and take the norm of that, the answer should be your scale by the absolute value, the norm of V. So norms don't have to be linear, they have to be sublinear, they have to have this scaling property. And the third point is like if the norm of V equals 0, then V should be equal to 0. And there's general theory here. So if you have a vector space with an inner product, then you can always take square root of inner product with itself, and that will always be a norm. And so I won't go through that like full general proof. I'll just tell you that for your reference. So the fact that this is an inner product with the definition of inner product that we gave last time immediately implies that this is a norm. So this is in complete analogy with like the inner product on vectors. Inner product on vectors is like the dot product. Dot product of x with itself and take the square root gives you the length of that vector or the norm of the vector. But it's completely general. And also, this is kind of an aside, but you can define a distance function. So given a norm, you can define a distance function given by the distance between f and g is equal to the norm of f minus g. So you can actually put a distance on the space of L2 functions. So what is it? It's a vector space, it's an inner product space, it's a space with a norm, and therefore it's a space with a distance function. It's sort of like the actual formula for it. And I won't write down all the properties the distance function has to satisfy, but I'll sort of say them. distance from f to g is equal to 0 if and only if f equals g. Distance from f to g should be equal to distance from g to f. You can see that. And it also has to satisfy this sublinear property or like a version of that. It has to satisfy this property that distance from like f to h is less than or equal to distance from f to g plus distance from g to h. So those three things in general make you a distance function. I'll just write it. So this last one was like distance from f to h has to be less than or equal to distance from f to g plus distance from g to h. Yeah, so it is similar to the triangle inequality. Yeah. So if you want to go from f to h, then it takes longer to stop somewhere else along the way. And if you're a set with a distance function, then that's what's called a metric space. So this is not just a vector space, it's also a metric space with this notion of distance on it, just like for your reference. But I don't know that we're going to use that in this class. I just think it's kind of cool. And about this point 3, there's this annoying fact that this isn't quite true, because if you look at the norm of f and say that's equal to 0, then this is like telling you, well, if the norm is equal to 0, certainly the norm squared is equal to 0. So that's telling you that you've got this equality. And something we've been over a couple times is, look, if f was continuous, then this equation would tell you that f is the 0 function. Of course, we're not looking at the vector space of continuous functions. We're looking at the, we're looking at the vector space of square integrable functions. So it could be true that f is non-zero on a point, or like on a discrete set of points. So f can be non-zero more formally on a set of measure 0. So for instance, like if you have a function that's like just equal to 0, that's equal to 1 maybe at the point 1/2, but equal to 0 everywhere else, then it'll be true that its integral is equal to 0, even though the function is not. You could even take a function that is non-zero, like on the Cantor set, and it'll still have 0 integral. You could take a function that's non-zero on all the rational numbers, 0 everywhere else. It'll still have 0 integral. So there's all these kind of like non-continuous functions that mess up this third property. And that's kind of where Lebesgue came in the early 20th century and did a lot of theory. You learn all about this in an analysis class. But what the end of the story is that you kind of just make this identification where you identify two functions together. If identify two functions together. One way to say it is two functions are identified if they only differ on a set of measure 0. To say it without using technical language, you can identify two functions together if their integral of the absolute value of their distance of absolute value of their distance from each other. So literally what it means is to consider the equivalence class. So the collection of equivalence classes of L2 functions, where two functions are in the same equivalence class, if and only if their difference is is 0 except on a set of measure 0, or if only if their difference satisfies this property. And that's something that I don't want to kind of get into like too deeply, but if you're familiar with equivalence relations and equivalence classes, that's formally what I'm saying. And the vector space under that identification will still be a vector space. And then this will be a proper norm on that proper vector space. But in practice, people just say that. Okay, it's in my mind, I said it, and then you shove it in the corner, and then you go back and keep on working like normal. So you just sort of like have that caveat in the back of your mind. There's a question.
What is a set of measure 0?
Yeah, what is a set of measure 0? I'm kind of saying all these things that invite questions about analysis, and yeah, I think it's fair. You know, if I said it, like it's fair to ask what it is, and I can just give you the answer. Basically, a subset of the real line is a set of measure 0 if the following is true. If it's possible to cover that set with a countable collection of intervals with the property that given any positive number you pick, you can choose this countable collection of intervals to have total length less than that number. So for instance, if I look at S equals 0 and unioned with 1 over n, then this is a set of measure 0. Because if you give me any tolerance or any positive number to represent the error, you know, call it epsilon, you give me some epsilon bigger than 0, then I can take a small interval about 0, you know, maybe of radius epsilon over 2. And then there will be like finitely many points left here. And I would just need to choose intervals about each one of those points so small that that finite sum was less than epsilon over 2. And in that way, I would have produced a collection of intervals that cover this set that was then less than the number that you prescribed. And since you can always cover it with intervals that are always less than any number you want, you would say the measure of that set is equal to 0. And in fact, there's a whole theory of measurement that then tells you how you can take like the length of something or the area of something, not just by, well, how do we know how to take areas so far? Rectangles, or if it's like the region between two continuous curves, you can do some like vector calculus thing. But there comes this huge issue later on. If you want to study probability or analysis or random motion or things like that, where you actually need to be able to ask yourself, like, can I measure more general sets? And the answer is yes. And this was basically Lebesgue's big contribution, sort of developing this measure theory. So identifying which subsets of the real line that you actually can measure, and more surprisingly, that there are some pathological subsets of the real line in which it doesn't make sense for them to have a length in any kind of like well-defined kind of way. And so that's for analysis 2. So if you take analysis 2 with me or anybody else, then you'll learn about like measure theory and Lebesgue integration. For here, it's just kind of a footnote so that I don't lie to you. You know, it's like I understand that this isn't exactly true. It is true under a technical identification. It just speaks to one of the myriad technical problems that you confront if you really try to do analysis or PDE. But you also can overcome them and get a nice, pretty theory. Okay, fine. And why? Do I want to say all this? Because I want to start talking about sets of orthonormal functions. So I want to consider maybe a set F1, F2, continuing on and on. So I'll just call it F sub n. So consider a sequence of functions, each one inside L2 of the interval. And suppose they're orthonormal. So suppose the inner product of any two of them is equal to 1 if n is equal to m and 0 else. And we've already seen examples of this. So we looked at this subspace V naught, and we found that the function Fn equals sine, well, in our context there, A was 0 and B was L, and then function Fn was equal to sine n pi x over L. And they weren't quite orthonormal because it was equal to like L over 2, but then you could just divide the function by L over 2, and then you would get an orthonormal set. So we've seen an example of an orthonormal set of functions before. And then we can ask the question, which is to say if f is inside L2 of interval from A to B, is it true that I can write this as a countable linear combination of functions f sub n? And the answer is going to be, it depends. You know, it depends a little bit about the functions that you pick, but we can still do a lot of work. It means, so you're countable if you can be written in an infinite list indexed by the first one, the second one, the third one, look at the fourth one. So more formally, a set is countable if there's a bijection between that set and the natural numbers. And so less formally, you know, when I say countable sum, I just mean like adding up, you know, 1 to 2 to 3 to 4, like all the way up to infinity. But we allow adding up to infinity, and that's still countable. There are sets that are uncountable. So the real numbers are not countable. There's no way to put them in a list, you know, like one coming after the another. Okay. Yeah, so the question was, what does it mean to be countable? And like in order to answer this question, well, last time we already did, like in a special case, we said that if f is equal to this sum, if I don't write this, assume it just means n goes from 1 to infinity, then you can just take the inner product with f and f m, right? And then by orthogonality, you'll just be left with so this is fm and this is f. By orthogonality, you'll just be right. You'll just be getting cm times fm, fm, And since it's orthonormal, like if this is a constant, then you can divide through by that constant. But since this is 1 by orthonormality, then you get this formula that the constant is just the inner product, which in this case is just going to be that norm squared. So it recovers for you the formula that we got last time in that special case. So I said, suppose that you've got, the question is, what does Fm represent? And I said, the answer is, suppose that you've got an orthonormal sequence of functions in your space. So under that supposition, if it's true that F is a linear combination, infinite linear combination of that, I hesitate to call it a basis, but but sort of like an analog of a basis from linear algebra. If F is a linear combination, then the coefficients have to have this formula. So this is a formula for the mth coefficient. Like Cm equals F, Fm. Okay. And so speaking of all of this, when you write down an equation like F is equal to an infinite sum, there are multiple ways that this can be true. So there's multiple ways for an infinite sum to converge. So remember from last time that this is equal to the limit of the corresponding sequence of partial sums. The corresponding sequence of partial sums for a series is given by just the sum of the first n terms. So whether or not this series converges to a function is exactly equivalent to saying whether or not the sequence of partial sums converges to the function. And so Sn, the sequence, this is itself simply a function from a to b. It is an element of this L2ab. So what you're saying, like, does this series converge to function f? What you're asking yourself is it true that this sequence of functions converges to function f? And in order to investigate that, we need to understand, like, the different ways that S sub n can converge to f. So I'll write that out. And one way, the way that you're maybe most familiar with is pointwise, which just says for all x. So for any x, or for all x, for fixed but arbitrary x, then it will be true that the limit as n goes to infinity, Sn of x equals f of x. So the problem with a function converging to another function is the fact that you've got a variable. So if you eliminate that problem by saying, okay, just declare that for any x, substitute in that value of x, and then this sequence of partial sums becomes an actual sequence of numbers, and then I can just take the calculus limit. It either exists or it doesn't. And if that limit is equal to f of x, then I say that this series converges pointwise. Give you an example of that in a minute. Another way you can conceptualize that, you can define maybe capital En of x, like call this the error, to be the absolute value of f of x minus s sub n of x. And you could say that, instead of that limit of s of n equals f of x, you could say that limit as n goes to infinity of the error is equal to 0. This is equivalent. This is equivalent to saying that the limit as n goes to infinity of Sn of x equals f of x. Well, why are they equivalent? There's a technical reason, but intuitively it's quite clear, because if this difference in absolute value is going to 0, then of course these two quantities are limiting towards each other. So you can think of this limiting to that, or you can think of the error limiting to 0. And a small remark, your book doesn't use absolute values here. So their definition of error is just like a little bit different. It's not going to affect anything though, but just so you know. Functions that converge to the same value as n goes to infinity. Maybe like rephrase the question. Yeah, sure. But this is pointwise convergence. So you would say that you would delimit that by saying that f is equal to this pointwise. And the next type of convergence that you can look at is convergence in norm. So you've got your sequence of functions Sn, and you've got a norm on this vector space. So you could define maybe like a new kind of error. Instead of plugging in a point and looking at the absolute value, you could now no longer plug in a point, but just look at the L2 norm of the difference between the function and the sequence of partial sums. These are two functions in L2. You can look at their norm. I'll even put it here for you. And you can say that Sn converges to f, like in the L2 sense, if now the limit as n goes to infinity of this error function equals 0. Basically what I'm getting at is there's different ways of measuring the error, which then lead to different ideas of when a function converges. And this is also called convergence in the mean square sense, because mean meaning like you're taking this integral, which is just like taking an average but without normalizing it, and then the square meaning that. So like you're averaging like this, on average for all different x's, you're taking the square of this error, and then you're integrating that. There's another kind of convergence, which is what you call uniform, which is like saying that whereas this convergence depends on x, like for one x, you might converge really fast. For another x, you might converge really slowly. If instead your convergence has the same uniform rate for every single x, then you have uniform convergence. And so what you do here, we'll call this error epsilon. And so this is going to be, what you do is you take the maximum over all x between a and b of the usual error, or the pointwise error. And more formally, it's the supremum of x going from a to b. So if you know about supremums, then that's the formal definition. Like if you try to take like S to be the open interval from 0 to 1, and you ask yourself, what's the maximum of S? Well, there is no maximum because you're not including the point 1. So like you can get close and close and close to 1 as you want, but you can't quite get there. And you solve this with this idea called a supremum, which just means like if you've got a little open endpoint like that, then just sneak on out to the limit point, and that's your supremum. So again, if you want to be an analyst or for being technical, you would say supremum, but intuitively, you're just taking the maximum of that error over all x in the interval. It'll either be bounded or it won't. If it's bounded, then you've got this nice definition. And if more than that, if as n goes to infinity, this error goes to 0, then that's called uniform. Convergence. So if the maximum pointwise error, so if the pointwise error, not just at one point, but at every single point is not just bounded, but also tending towards 0, then you can say that your functions S sub n are converging towards f in that uniform manner. And I'll show you some examples to like try to keep it straight. So first of all, uniform is the strongest kind of these three kinds of convergence. So if like the limit of the SNs is equal to f uniformly. So when I say this, I mean that your series is equal to f uniformly. I mean that if the sequence of functions converges to f uniformly, therefore I mean that if this error is going to 0 as n goes to infinity, then it'll also be true that Sn goes to f pointwise, and that Sn goes to f in the mean square sense or in the L2 sense. And how can you show that? Well, certainly you can argue this really quickly. So the pointwise error for any x is always going to be less than the uniform error, because this difference, pick an x, look at that difference, it's certainly going to be less than the maximum difference for any x. So if you're converging uniformly, then in particular, for any fixed point, your pointwise error must be going to 0, and therefore you're converging pointwise. So just having this bound between the two automatically says that uniform convergence implies pointwise convergence. That's why I use an absolute value in my definition of pointwise error. This would not be enough to show convergence if I didn't use that absolute value there. Okay, now what about convergence in L2? So I want to bound this other error, E sub n, which is over there. Maybe I'll even square it. Well, actually I won't square it, I'll just leave it alone for now. So how can I get control over this? Well, I think that this integrand for any x, f of x minus Sn of x, that's just En, right? Or even just straight up equal to, because that's just definition of En. But now, for any x, that pointwise error is certainly less than the maximum of all of them. And so you can pull out the constant and you just get epsilon n times integral of the number 1 from a to b dx raised to the 1/2. And integral from a to b is like b minus a. So you get something like square root of b minus a times this other error is bigger than or equal to the mean square error. And so if this is going to 0, if you're converging uniformly, then automatically you're converging in the L2 sense or the mean square sense. On the other hand, it's certainly possible to have differences between the other two. So there's a classic example where if you take Sn of x to be something like x to the n, yeah, sure, you'd have to think about how you would arrange your like f1, f2, f3 to make them like add up to this, but what is Sn of x? Like it's a function in L2 from a to b that depends on x and is indexed by n. So I'm giving you an example to illustrate like how the convergence works and try to keep them simple as possible. And so this converges to a function f pointwise. And which function does it converge to? So it converges to the number 1 if, for this example, I'll take AB equals interval from 0 to 1. So this converges to 1 if x equals 1, right? Because your right-hand endpoint is always constant, it's always equal to 1 no matter what. Converges to 0 else. So you can look at a typical one of these functions and they smoothly go from 0 up to 1. And as n gets bigger, functions tend to look, more and more and more like that. So each point x, they'll drop down and converge to 0, except for this point, which will stay 1. But for all the other points less than 1, eventually all these will head down to 0, giving you that pointwise limit. So it's pretty easy to check that limit as n goes to infinity of x to the n is equal to 1 if x is equal to 1. And it's equal to 0 if you're between there, because you're like decreasing your magnitude by a definite amount each time, heading closer and closer to 0. On the other hand, this convergence is not uniform, because if you look at this maximum deviation, and I'll just do it pictorially here, but like take a typical example of Sn, maybe looking like that. So for any particular x, like for this x in the middle here, the difference between f of x and Sn of x is small. So if you fix x, that difference will get smaller and smaller and go to 0. But for any one of these xn's that you pick, if you now allow x to vary from 0 to 1, and then look at the maximum of those errors. So this is your function capital En of x, and it changes with x, right? Because it just gives you that length. And since this function is continuous, there's always going to be some value of x, for instance, when this error, so that this error is like, yeah, or certainly like bigger than a half, right? But yeah, bigger than any constant less than 1 that you pick. And so I can bound this error from below by like 1/2. So in particular, this uniform error, it's like bigger than or equal to some fixed number, no matter, like independent of n. So when you take the limit, it will not go to 0. So this is an example of a sequence of functions converging to a limit pointwise, but it does not converge uniformly. I'll give you another example that I like to clarify the other difference, which is take Sn of x to be the following function. It's going to be 1, and I'll maybe just define this for n bigger than or equal to 2. It's going to be 1 if I'll say that, like, so what's my ranges for x? So it's going to be equal to 1 if x is bigger than 1/2 minus 1 over n, and less than 1/2 plus 1 over n, and 0. Else, so a typical one of these functions looks like that. And it's quite clear that the pointwise limit is going to be 1 if x is equal to 1/2 and 0 else. Because this point 1/2 is always equal to 1 no matter which n you pick. But for any other point x, you can always find an n so large that 1 over n will be smaller than it. And so for all but the first finitely many terms, Sn will just be 0. So the pointwise limit is either 1 if x is equal to 1/2 or 0 everywhere else. On the other hand, the mean square limit of this I think is just the 0 function. So Sn converges to f pointwise, but Sn converges to 0. In L2, and like, why is that so? Because if you write down the mean square error, then this is something like, even write down the square of it just to get rid of the absolute of the square root. This is something like integral from 0 to 1, working again on this interval AB equals 0, 1. And so you look at what the difference between your limit and S sub n, here your limit function is 0. So you're just looking at absolute value of S sub n, but S sub n is positive, so you're just looking at S sub n squared. Dx, S sub n squared is equal to S sub n because you're either 1 or 0. And so now this integral is just the area under the curve, which is like base times height, which is, base is 2 over n, height is equal to 1. And this error goes to 0, which proves that that's what convergence means when the associated error goes to 0, which proves that this function converges to 0 in L2, meaning when you take all the errors and take the integral, it goes to 0. But it converges to this other function f, pointwise, which again makes perfect sense because this error involves an integral, and the integrals can't detect the value of a function at a certain point. In fact, they can't detect the value of a point on an entire set of measures 0. So you could have cooked up an example where, where the limit was actually like equal to 1 on the Cantor set or something like that. So you can get like more complicated examples or something, but this illustrates the typical way that a function might fail to converge, might have different limits depending upon which notion of convergence that you use. Maybe it converges in one setting, but not in another setting. So I hate to just dump a whole analysis type lecture on you, but since we did organically get into this idea of trying to write a function as a sum of an infinite series, we do now have to investigate how can that be true, and it will come, the different ways of convergence will make a difference, and we'll see that in our examples. Okay, but this is just to sort of get us on a baseline. So thank you everybody for your time and attention, and I'll see you on Friday.